So today we're going to continue with partial fractions, but now we're going to consider the case when the function has something like this, where there's a square term. When you factor it out, if you end up with a square, or even cube, or whatever it is, but a power larger than 1. So we'll look at that. All right, so how are we going to do this? Well, remember in the previous video, I told you that you would want to, so let's do here aside. And remember last time I told you that you wanted to write this expression, so 7x plus 11 over x minus 1, x plus 2 squared. You'd want to write it in a way where you would pick, for the first one is no problem, because it's linear, so you want something of degree 1 less. So you could potentially just say, well, I'm going to pick bx plus c and divide it by x plus 2 squared, and that would be okay. However, your integral would not be as easy to compute, because then you have to look at a u substitution here and split this term into things that would work for you. So the best way to do it is the following. It's going to allow you to compute your coefficients in a way that after you compute them, your integral will be easy to compute. Because this one, again, is going to be just a natural log. And then whenever you do a u substitution here, you get u to negative 2, which is going to give you an integral of negative u to negative 1. So it's going to be easy to integrate. So we're going to favor this setup. So I'm just going to, what happens, for example, if I had a cube? Let's just do that for as an example. Well, then you just continue increasing your degree by 1 until you get to the one that you have. But we don't have any of that, so let's just not do that this time. But that's how you would address it anyways. So you're just going to keep adding b over x plus 2 degree 1, then c over x plus 2 degree 2. You had 3, you go to degree 3. All right, so then to do this one, this coefficient, you can still use the Heaviside approach. So for a is going to be equal to this 7x plus 11 over x plus 2. I'm ignoring the x minus 1, the one that makes it 0. I'm ignoring that one, and I'm going to evaluate it at x equals to 1. So that's going to be 7 plus 11 is 18 over 1 plus 2, which is going to be 3. I'm evaluating at 1 squared, that's a 9. So I'm going to get a 2 for that coefficient. So that coefficient is easy to obtain. Now, the next one, you got to be a little bit careful, because b, you will not be able to obtain. You will be able to obtain c. And why is that? Because if I were to multiply everything times x plus 2 squared, when I evaluate it at negative 2, this one, it'll cancel. So in the limit, it still would be 0, but I'll get the same result as with direct evaluation. But this one right here, when I do the square, I would cancel it out, and then I would get the value of c. So that one I can do with that value, I can do with the Heaviside approach, and then I'll tell you how to do the other one. All right, so now c, the one I can compute by just evaluating 7x plus 11 over x minus 1. So I'm ignoring this whole thing, which is the one that makes that one 0. But I can only do it for the largest degree. I cannot do it otherwise. And I want to evaluate at negative 2. That's what makes that equal to 0. And when I do that, then I get negative 14 plus 11. Let's write it out. It's negative 2 times 7. And then I'm going to have negative 2 minus 1. What I'm going to get here is going to be negative 3 over negative 3 is positive 1 for this one. So I get A and C sort of for free just by doing the Heaviside method. So what I'm going to do here now is I'm going to clear all the denominators. So for B, at that point, you're going to do the method we did at first. So 7x plus 11 equals, and when you multiply everything, I'm multiplying everything times x minus 1 times x plus 2, here I get a times x plus 2 squared, and then here I'm going to have b. I'm going to cancel because in the limit I'm still going to be able to evaluate, but I'm not going to evaluate at -2, so no concerns there, plus c. So I have those values there. And then what I'm going to try to do, you see, evaluating at -2 is not going to help me because that's going to give me my c. I already know what c is. I need b. So at this point, you can evaluate at any other number, but remember that you already have a and c. So a is going to take the value of 2, so we can replace it. And c is taking the value of 1, so you can just replace it. And then now you have b that you have to evaluate, and the easiest thing to evaluate at perhaps could be 0, or if you want, you could also do -1, so you get ones around. I'm going to evaluate at x equals 0 because, well, why not? Now, the one thing is you're going to do, what you don't want to use is evaluate at 1 or -2 because those you already used, and also you know what they would give you, so you don't need those values. So you evaluate at x equals 0. So on left hand side I get 11. This one I get 2 times 2 squared, so it's going to be 2 times 4, not 24, 2 times 4. And then plus b, which is the one I need, times 2, so 2b plus 1. So let's subtract on left hand side what I have here. So I have an 8 and a 1 is a 9. So I'm going to subtract a 9 on both sides. When I subtract my 9 on both sides, I get 2 equals 2b. And then b is going to be equals to 1. Equal to 1. Did I do that right? Minus 9. Yes. Okay, so b equals to 1. I was uncomfortable with this for a reason, and that is because you see when I multiplied here, I have the x minus 1 times x plus 2, and the first x minus 1 cancels, but the x minus 1 does not cancel in these terms. I was a little confused as to what was happening. And so I went ahead and paused and I checked. So when I evaluate at 0, you see this one becomes negative. Thank goodness I checked. And this one, when you evaluate at 0, also becomes negative. So then this is not going to be a 9 because you're going to have 8 minus 1 is going to be 7. So I'm going to have to subtract 7 on both sides. And that makes more sense because I had previously computed the numbers that I was supposed to get. You know, we cooked before the video. So I was supposed to get b equals to 2, and I was -2 rather, and I was a little surprised that I was not getting that, so I had to stop and check. So be careful because I was multiplying times this whole denominator, but then when I went ahead and multiplied here, I forgot my x minus 1. So just with that, then I get -2 as I was supposed to. So apologies for that, but this is the approach that you will be doing. So with that in place, then you will just copy this, and your integral will become the integral what I had already, where I started. Whenever we write these problems, we usually will start with something so that your numbers are going to be nice. We start the way I did it in the previous video. We start with something that is nice, and then we work backwards. At least that's how I do it. Maybe other people don't do that. But that's the way I do it, so that I know that the numbers you get are going to be nice. So you don't end up with fractions that have like a 17th and a 13th and things like those. Not that there's anything wrong with it, but I just don't like them, so that's why I avoid them. In any case, now I can integrate these ones. So 2 natural log, use substitutions, all of them. So remember that we get too comfortable with these when we do partial fractions, because usually when we factor things out, they don't have other coefficient other than a 1 in front. So du equals dx, so there's no constant to play with, but you have to be careful with that. So then this one is going to be u to the -2, as I said, so plus 1 is -1. So the integral is going to be just the 1 over x plus 2. That's going to be the derivative of that. Excuse me, plus c. And so like that, we get the integral whenever I just wanted to illustrate when you have a square, when you have a how do you address that? So now we're going to address the other situation. That would be when you have squares, but when the squares come from, and let me pause here, when they come from an irreducible polynomial. So let me stop right here, or pause. Okay, so what kind of things do we need here? Well, let's say we have an x, I like x minus 1 apparently, so let's leave that. And then a polynomial that you cannot factor, so x squared plus 1, something just straight up like that, dx. And then I'll do the number so we get a nice numerator, so the numbers work out okay. All right, so let's do something like this. So the way you're going to do this type of problem, now you cannot, you see you don't have a square outside, you have a square there. And this, of course, the reason why I say is irreducible is because if you were to try to find the roots of this polynomial are they're complex or imaginary, so you're not going to be able to split this into x minus something. So that's something being real. You could do plus minus I if you want, but that's not going to help us to integrate here. So that's not what we need. So the way you're going to address that then is you're going to do the same thing I told you for the linear term. Even though it doesn't look the same, it is the same, because you're going to write a polynomial of degree 1 less to whatever you have. So in the case of the square, for the first one, well, x minus 1 is a polynomial of degree 1, so you pick something of degree 0, so a, done. And then the other one is a polynomial of degree 2, plus 1, sorry, and you pick something of degree 1. Well, not a, because I already used a, so bx plus c. So you just use something that is of degree 1, and the most general polynomial of degree 1 would just be bx plus c, where b and c are constants that you don't know. And so now, how do you address it? Well, a, you do the same way, because you can do Heaviside method for that one. So you can just say it's going to be x squared minus 3x plus 4 over x squared plus 1 evaluated at x equals to 1, because that's what kills this term in the denominator. And that whole thing gives us what? We use 1 minus 3 plus 4, which I was adding incorrectly. I'm like, I got 0. No, never mind. 1 plus 4 is 5 minus 3 is 2 over 1 squared plus 1 is 2 again, which I get a 1. So just evaluating that, I get a 1. Perfect. And now for b, well, there's a bit of a problem, because you have nothing that makes, or b and c, there's nothing that you have that makes this equal to 0. So what you can do, you can go on to just evaluating, so multiplying everything across times the denominator. So the x minus 1 cancels here, and I'm going to be careful this time. I'm not going to be silly like before, I promise. Or I'll try not to. And then when I multiply here, oh, this one is going to be just bx plus c. There's not much confusion there because there's no square. So this one cancels, and I get x minus 1. All right, so I know that a is 1. I can replace that. I don't have to have that written. So in fact, there's that. When a is equal to 1, this looks like this. So I have that very nicely. So you can start plugging in numbers. So you can plug, say, x equals to 0, and then you get equations for x equals 0 is nice because it's going to kill the b. You're just going to directly evaluate c. And so that's going to give you something very straightforward to do. And I'm annoyed at myself that I'm not going to do it, because that's the easiest way to do it. But some people don't like just picking. Some people don't like freedom. Controversial topic there. But in mathematics, meaning that people don't like just plugging a number, and they say, which number do I plug? Well, you don't have to. So the way if you don't want to pick a number, the way you would do this is you can FOIL this out. So you get the bx squared. Now for the linear term, you have a c minus b. Once you FOIL it out and you factor, you're gonna have a c minus b, sorry. That comes from c multiplying x, and then minus, or bx multiplying -1 is c minus b times x, and then the constant term is just going to be minus c. So what then you would do is you notice that you can equate coefficients. So for example, what coefficients multiply the x squared? So there's just those x squared, and what I can write is an equation that tells me that 1 equals the coefficient of the x squared. I'm equating the coefficients of the x squared. Let's go write cube. So equating the coefficients of the x squared, I get 1 equals 1 plus b. And that automatically tells me that b is equal to 0 when I subtract on both sides. With b equals to 0, I can then plug it in here into my equation. So I can just eliminate that, and I can eliminate that. And now I can just look at equating, for example, the linear term. So just equating x, I get on left-hand side, I get -3. And in right-hand side, the only x that I have is c. So c equals -3. So I get my numbers like that. As I said, if I were to do it, I'll just plug x equals 0 and then x equals another number and get my two constants b and c. But some people don't like that freedom. They feel like it's a little bit sketchy, so to speak. And so that's what it is. So if you don't like it that way, you can FOIL everything out and then equate coefficients for the powers of x. And that is, you're basically using the fact that the powers of x are linearly independent set. And that is what justifies that approach. In any case, that's the third approach I kept advertising to finding the coefficients that I wouldn't do, but just in case some people would like to do it that way, I put it out so you also know how to do it. So using the coefficients that we obtained, this is written as the integral of 1 over x minus 1, that was my a. Then b was 0, so I just get, and sorry, I was going to write plus, but c was -3 if I remember correctly. So 3 over x squared plus 1. And then when I integrate here, I get the natural log of the absolute value of x minus 1. And here -3 times, and this is just straight up an arctangent of x, the integral. So that one we didn't need trigonometric substitution, but we could. If here we would have had something a little bit more exciting, perhaps. No, not really. That's just an arctangent. Anyway, so that's right there our last two examples for the partial fractions. I thought it would take another video, but hey, that's good. We did it all in one. All right, well, thank you for watching, and I'll see you in the next video.